Hello everyone. So the today's topic is magnetic boundary conditions. So in the magnetic field, so the boundary conditions between two different magnetic materials are given below. The tangential component of magnetic field intensity is continuous across the boundary. Second case is the normal component of magnetic flux density is continuous across the boundary. So consider the boundary between two isotropic homogeneous media with permeability of mu1 and mu2 as shown in figure. So this is the boundary between two magnetic media. So we have considered as a mu1 and mu2 from the different medium 1 and medium 2. Then horizontal is del x and vertical is del y. Then we have to derive the boundary conditions so between the two magnetic media. So consider a small rectangular of width del x and length del y at the boundary of two media. Let Ht1 is the tangential component of magnetic field in the medium 1 and Ht2 is the tangential component of magnetic field in the medium 2. According to the Ampere's law, so we know that integral of H dot dl equal to total current enclosed by the path. So that is H dot dl equal to I. If there is no current enclosed by the path, means the current is 0. So closed integral of H dot dl equal to 0. So from these equations we have to obtain that equation Ht1 into del y minus Ht2 into del y equal to 0. So from these equations we have to obtain Ht1 equal to Ht2. The tangential component of H in the medium 1 is same as medium 2. So that is the tangential component of H is continuous across the boundary. So next case, consider a pillbox of surface area ds across the boundary between two isotropic homogeneous media as shown in figure. Let Bn1 is be the normal component of the magnetic flux density in the medium 1 and Bn2 be the normal component of magnetic flux density in the medium 2. By applying the Gauss law for magnetic field, so surface integral of that is called as a double integral of B dot ds equal to 0. So from these equations we have to use with that normal component as Bn1 into ds minus Bn2 into ds equal to 0. So from these equations we have to obtain with that Bn1 equal to Bn2. So that is the normal component of B is continuous across the boundary. So next case, consider the magnetic lines away from the normal across the boundary as shown in figure. So we have to represent the figure pillbox of the boundary between the two magnetic media. So from this mu1 and mu2 is the two different medium. Bn1 equal to B1 cos theta 1 and Bn2 equal to B2 cos theta 2. But we already derived as Bn1 equal to Bn2. So that's then B1 cos theta 1 equal to B2 cos theta 2. So that is the equation number 1. So from this boundary surface between the two magnetic field, from the relations between the magnetic field intensity and the magnetic flux density, Ht1 equal to Bt1 divided by mu1. So same case for Ht2 equal to Bt2 divided by mu2. So from this figure Bt1 equal to B1 sin theta 1 and also Bt2 equal to B2 sin theta 2. Substituting these value in the above equation, mu2 B1 sin theta 1 equal to mu1 B2 sin theta 2. So divide the equation 2 by 1. So mu2 B1 sin theta 1 divided by B1 cos theta 1, which will be equal to mu1 B2 sin theta 2 divided by B2 cos theta 2. So from these equations mu2 tan theta 1 equal to mu1 into tan theta 2. So therefore the tan theta 1 divided by tan theta 2 equal to mu1 by mu2. So this is the case we have to use with that boundary surface between the two magnetic field in that normal component and the tangential component. For the normal component we have to use with that Bn1 equal to Bn2. Whereas a tangential component we are used with that Ht1 equal to Ht2. So from these equations and also we are using with that angle declination is taken place by the magnetic material. So from this equation we are obtained with that tan theta 1 divided by tan theta 2 equal to mu1 by mu2. So this is the magnetic field that is a magnetic field in the boundary conditions between the two different magnetic medium, that is mu1 and mu2. So thank you.